I would say that vapor. We're talking about the medium we're in. When you heat that up to cause the vapor, that's all the gas is being heated up to make a vapor, if you will.
Does anyone else have an answer?
I think it's all one medium, just at different states. It's all fluid.
So you're going to say vapor and gases are all fluid?
Yep.
I would say fluids are generally liquids and gases are not. And vapor, I don't think is a liquid. I think vapor comes from a liquid, but it's not in a liquid state. So I wouldn't necessarily agree with that.
No, I just said that the gases that are heated up
Yeah, we heard you, Jim.
transition into vapor. So the medium we're in can be heated up to make vapor.
We heard you, but not everything requires heat to make vapor. For example, like butane, right? In a condensed pressurized version is a liquid, and it boils off at a very low temperature, which wouldn't necessarily be considered heat, right? So it goes from a liquid state to a gas state. But when it goes to the gas state, is that now vapor or is that gas? Is there a difference between the two?
It's vapor.
I'm looking for an actual answer.
Vapor gas.
Yeah, I'm looking for an actual answer, not just like what you feel.
In some cases, a vapor is considered to be what would normally be a liquid at a given temperature, but exists in a gaseous state. An example would be water vapor in the atmosphere. If the temperature is, say, 70 degrees Fahrenheit, the oxygen and nitrogen and other gases in the air are well above the boiling point of those gases. But you could have water in the air. It's a gaseous form, even though it's well above the normally it's below the boiling point, so it exists typically as a liquid rather than as a gas. That's the way I understand vapor being a bit different from a gas.
So you would say that they're distinctly different?
It's difficult to say because people use those terms interchangeably, but many times in thermodynamics you talk about, to say vapor pressure, and it's at that point it's talking about a substance that normally would be in a liquid state but exists in a gaseous state.
Let me ask you something, Danny. Would you consider the call it atmosphere in your thing, would you consider it one medium?
It depends.
On what?
When talking about Snell's law, the difference between media is referring to the difference in the index of refraction. If you have two layers of the air that have different indices of refraction, they can be considered two different media, even though they may have the same composition.
Be considered, that's the important word, but it's still the same media, the same medium. Would you agree to that?
But in conjunction with Snell's law, there is a big difference there.
Yeah, well, if you want to think of it at what Snell's law, but in reality, even if you consider Snell's law, it's still one medium, the atmos.
Well,
it's just considered different rates of.
You'd have to be very careful then how you state and use Snell's law, because Snell's law oftentimes is talking about refraction occurring between two different mediums. The word medium there doesn't refer to substance, chemical composition. It's referring to indices of refraction and nothing else.
Okay, so not an actual physical thing. It's just an appearance. Like for example, heat haze. You can consider that as a different medium then.
What was that again?
Heat haze, when the heat rises and it causes like a wavy type.
Yeah. And again, the word medium can have different connotations in different contexts. Generally, we think of a medium as two media being different chemically from one another, but with regard to Snell's law, you need to be careful to make a distinction there that it's really referring to the indices of refraction involved,
and not an actual substance like water or atmos, just how it looks, basically.
Oh, no, it's just talking about the index of refraction, which depends upon the speed of light in that substance.
Right, but it would be the same substance, but due to a different temperature in this case, what you're saying, no?
Yes, yes.
Okay,
And
all
an
right.
earlier question was asked. Someone said that they thought of liquids as being fluids and gases are not. Actually, both liquids and gases are fluids. The difference is that gases are compressible and liquids generally are not.
Okay, so just as long as we make the distinction, like a medium, for example, the atmos and the water, those would be considered two different mediums. You agree,
And
Danny?
in every context, they would be yes.
Okay. So now back to the single medium, which we said was the atmos, right? Now, when you bring Snell's law into that, you can see like there's a little bit of a problem there. You would have to consider what's happening in the single medium in the case of different pressures or different temperatures, but definitely not a different medium. Well, that's how I
If we
would
were able
interpret
to travel, okay, what about when we travel, if we could travel through the medium into the vacuum? Is the vacuum considered a medium?
Well,
Not
that's
perfect,
fantasy la la land there. That's a whole
but
different.
it's got things in there that are dangerous. Okay. So it's just a vacuum. That's it, not a medium.
Well,
What kind of
that's a whole
vacuum? Like a
different
Hoover?
question. Yeah. So you see, it's kind of well. First of all, mic check. Can you guys hear me?
Can hear you, dude, but I think we kind of danced past the point that I was trying to make with the difference between vapor and gases. And Jen, you got a lot of lag. But anyhow, I got to get back to work.
Okay, I was just checking because my thing is doing crazy things today. See, we're even having issues defining a medium. So, I mean, yeah.
I think the problem is you're trying to define medium in one way that fits in every circumstance, and that's problematic because the word medium can have different connotations in different contexts. In general colloquial usage, a medium is a different substance chemically. In Snell's law, the two different media may have the same chemical uh, composition, but the indices of refraction are going to be different. So in that sense, again, Snell's law, you need to be careful what you mean.
Well, that's the problem. There should be one definition for something when we talk about it in context. That's why we should define terms before we even. That's why I even said let's define medium because we were going all over the place, right?
Well, you should define the word terms you use in terms of the context in which you're using them. Words can have multiple meanings depending on the context.
Exactly. That's why you should define terms before the conversation. So in this case, if a medium means a certain thing like gas or water, then Snell's law will not apply. Because if we define medium, like for example, the atmos and water, two distinct different mediums, then how can you make the same case in the atmos? It's clearly one medium, right? That's why, like, the physics is important. Look at the physics and then listen to what they say. It usually doesn't. The picture doesn't add up, like Rakia says. Picture doesn't add up. When you're playing cards and you see something's wrong, right? Picture doesn't add up. Well, picture doesn't add up here. And I've been saying this for years. For years.
It also seems like if you're trying to deceive, right, especially deceive the masses in the way things are described in context, you would use the same words with different definitions and just use them in different contexts and never describe the different definition. Just medium this, medium that, and in this medium. And in one context, you're not even talking about the physical medium. You're talking about the refraction index. And then everybody that really doesn't look into it or hear this or remember it, and even he would probably get people that disagree with him, disagree with him anyway. And that confuses people even more. How do you know it's even true? It is confusing though. I always thought medium was like water and air. They're two different mediums, right? But you can have two different mediums in the air if the refraction index is different.
Yeah, that's why you gotta define what a medium is before you go on. And the way I understand medium, it just, Snell's law wouldn't apply there.
What if you're in the air, right, where the birds fly, let's say, and that spans, right? And you go up and down due to temperature and pressure, you have different density layers and you can fly easier and further and faster and get lower to the surface where it meets the water and it gets thicker and thicker and thicker until you hit the water and then sploosh, right? You enter a totally different medium where the same energy stops you, right? Like it takes way more energy to move the same speed because you're in a different medium. But then when you exit the water, the same amount of energy moves you one speed, and as you go up in that medium, the same amount of energy moves you quicker and quicker and quicker until you reach a different medium where you might hit a thicker medium or a barrier or whatever. That's why I say it's all one medium. It's just different stages of that medium. So whether you want to call it fluid or whatever, like
that's
that
what I
makes
think,
sense.
bro. Yeah, that's what I think. Yeah. It's the same medium, but I would distinguish the water from the air. But I get what you're saying; it evaporates and so on and so forth. So yeah.
Even in the oceans, right? They say they go down to a certain depth and they hit a different medium, right? It becomes this, different fluid or something they can't penetrate, right? It's thicker and thicker. Whatever they call that.
Yeah. I brought that example up before. Yeah.
So as you go up in the air, you all of a sudden reach a different medium where it might get thicker and thicker and create a barrier. That's what I believe. As above, so below.
Yeah, but what I'm saying is it's the same medium and different pressures or different heat causing a different thing, but it's the same medium. Like water would be the same medium. But that's the way I see it anyways. But you can easily make the argument that water does evaporate and go into the air, and you can easily make that argument too.
They don't listen to you or try and understand what you're saying. So.
Can you not hear me good?
I was making a joke. I hear you fine. I just don't listen to you.
Oh yeah, okay. That's a different story because I've been having technical difficulties today. Nice below the belt, Eric. Yeah, I like it. Good.
Yeah. We had a group of people on a plane talking about flat Earth on the way home from Vegas the other night because I got them to look at the horizon, right? Define it. So they all define horizon pretty well as a horizontal outlay of where you see the sky meeting the ground in the distance. Surprisingly, pretty much everyone kind of defined it in that way or agreed to that definition. And I said, okay, look out to your right, out of the port side window. Does that horizon appear to rise towards your eye level, or are you looking down at it or whatever? And they said, well, we're looking down at an angle, but it does appear to rise to my, where I'm looking at, like out in the distance. So, okay, look out the starboard side of the plane. Does that appear to rise?
Isn't the starboard side the right side?
Yeah.
Okay.
Yeah, I might have it backwards. But anyway, you get my point. And they all agreed. Now that doesn't really prove anything, but they had never really noticed that before. But it was a fun conversation. People are something to do on a plane anyway, besides talk about sports or whatever.
I was just talking last night with a gal that I was at dinner with, and we were talking about the flat Earth stuff. And she goes, "Yeah, you can just look at a plane and see the curve of the Earth." I go, "No, you really can't." "Well, yeah, see it arcing up. Look out the horizon to the right, and then look out straight ahead and look out the other window. It's all a certain degrees below eye level." That's where we kind of disagree, you and me, Rick. Yeah. But bottom line was, it's all the same angle down, so it can't be curving if it's the same angle down from eye level all the way around you. It has to be a flat horizontal plane or a flat circle, hula hoop, as I would say.
But even I would agree on a sphere really large. The optical phenomena could create that, right? Like where it could look like a plane and actually be a sphere.
You mean Home Depot? The Home Depot bit becoming a sphere?
Yeah, you
That's
know
the
what I'm
difference.
saying. I
Though.
mean,
The
it could
Globers
work.
would never admit. The Globers would never admit it could be a plane and look like a sphere. Like you could admit, okay, it could be a big sphere but look like a plane. The Globers would never admit it could be a plane but look like a sphere. It's because
But
the
they
Snells,
do
right?
admit it.
That's quite dishonest.
They don't admit
It
that.
could be a sphere and appear to look like a plane under an optical phenomenon. Why wouldn't I?
I've never heard a Glober say it could be a plane but look like a sphere. They always say it could be a sphere but look like a plane.
Well,
I think
isn't that
Xanax would
Never heard it vice versa.
say it
isn't
for
it
him, Xanax.
Jaron's argument? The Home Depot side by side? Isn't that what they go with?
They go with it's a sphere, but it could look like a plane. But they've never said what Rocky had just said. But they've never said it the other way, where it could be a plane but look like a sphere.
Well, sure.
And
Don't they say that up to 100 square miles in that it looks like a plane? Don't they say that? Isn't that what they've been saying for
yes,
years?
dude. You're not. Are you hearing what I'm saying? They're saying it. They'll say it's a sphere, but it looks like a plane. But they'll never say it's a plane, but looks like a sphere.
Okay, I guess. But isn't that what they're saying when they say that the
Nope.
100-mile thing?
No, they'll never say what the thing I'm saying. The thing I said that I've never heard anyone say. They'll never say it.
What plane looks like a sphere?
Basically, what Neil deGrasse said, that horizontal lines can appear to be a curving under certain circumstances, like when you use a certain lens or you look out over the distance under certain conditions. Horizontal lines can appear to curve.
Yeah, with lens distortion, yeah.
I think that would, if you believe that would have to work both ways, right? Also, a curved line, either direction, convex or concave, would under the right conditions appear to be a horizontal line.
Yeah,
Well,
with the
Neil
right
deGrasse
lens,
Tyson has
yeah.
not been in a spaceship. Neil deGrasse Tyson hasn't been in a spaceship. He always talks about that shit is curved, man. You get an airplane, see the curve. They're all lying. They're just kind of assuming that because they always see all these pictures, and the pictures due to perspective shows the curve around you looking like it's curving down from the middle to the edges, because that's how perspective works on a flat 2D picture. But if you think about it, and not very many people do, it's a flat, horizontal circle around you, like a hula hoop.
Are you just trying to debunk Jeremy's claim that no Glover would say what you just said? You just trying to get
No,
under his
that
skin?
Zhang's a
'cause
flat earther now. He just doesn't
yeah.
want to
Well,
So
complain.
Jeremy's saying it, people don't say it looks flat, but it could be curved, or it could be flat, but it looks curved. I don't know about if you're saying it's flat, it looks curved. I never heard anyone say that, and he's right. I agree with you. No
You
one's ever
just
said
said
that.
it, man. You just well, it
No, I
sounded like
said
you
it.
said it.
I said it, but
No,
I've
they're
never
saying it's a
heard
ball.
people say that.
Yeah, they've always said it's a giant ball, but it looks flat. But no Glover's ever said it could be flat, but look like a ball.
Right.
They'll
Because
never
it
say
is.
that. They'll never say that.
Just that area, Zanuck, like that area that you're in when you're like in the helicopter or whatever. It's like the circle around you. That's definitely. I mean, I don't know. It's like a planar, or due to perspective, it looks like it's curving, or
Yeah. Oh, yeah. Due to perspective, looking at curving, but it's definitely a flat, flat circle around you with no curve to it. It's like you cut the top of a cone, cut the top of a cone off, and you have a flat plane. Now we don't. People that believe in the globe Earth will not say that that cone is flat, but the ring around the cone is flat, whether it be off of a cone or off of a sphere. It doesn't really matter. They're always going to be flat. That's the best analogy and description I can give you.
I look at it the same way, but we're in the middle of two cones, like a bubble, and we're on the flat plane in the middle. We live on the plane in the middle, and then the sky is curved above us.
Okay. What tests would you conjure up to kind of prove that to yourself? What would be a couple tests that you could do?
I would measure static water.
At what scale? Just in a glass in your cool backyard?
I would start as like as large as I could be accurate, and try and do more. And if I can't do it, then I would just have to logically deduce.
Why can't you
what I
measure
need
it? Why
the
can't you?
water to do.
If you think that there's a dome, let's say there's a dome above, we have flat surface and a dome above us, and that's what you think. And I said provide some tests that maybe you could prove that to yourself. So some of the proof mathematically, geometrically would be, how do you prove certain things in the sky or on the dome? You're flat, and they're on the surface of the dome. You could do tests trigonometrically by moving around on that flat surface and take measurements of things on the dome. If the sky is the dome and it has those stars and light and things on it, couldn't you?
Well, I can do that, but I don't know all the variables. I can assume I know all the variables and measure that way and deduce. But like if I go to my local church in my community that has a dome roof, right? I can measure the slab to be flat and the dome to curve at a certain rate because I can physically measure it. But I can't go to the dome in the sky. I can only measure to lights in the sky, which is what you're insinuating I should do. I would never do that personally. If I wanted to measure that dome over that church, I wouldn't measure the lights shining down and reflecting and refracting and doing whatever. I would want to measure the physical dome to know what the physical curvature rate of that dome is, or I would measure the surface of the slab to know whether it was horizontal or curving or not. That's just me, though.
But yet we measure things like clouds. You can do this test too. If you can find two people that are really far apart, but you can still see the same cloud, and say, hey, I'm measuring this angle to this cloud. Is this? And it looks like kind of it's a real dark cloud. It looks like a thunder cloud, maybe a thunder cloud. Be more, more accurate. Like clouds might be different shapes when you're right under them than they are far away. If you're getting rained on, you can see a thunderstorm in the middle of nowhere, and you call your friend, hey, is that thing over your head? He goes, yeah. And you measure the bottom of that thunder cloud, and you get a value angle, and then you say, yeah, this thunder cloud's above my head, I'm pouring, and it's such and such height above me. Wouldn't that kind of, if the angles are not according to the height of the bottom of these thunderclouds, which they usually are 3,000 or 4,000 feet. That would kind of throw a stick in the gears of.
Well, for you it might, but for me, unless I measured the elevation change of where each person was standing, I wouldn't know if the angle change was caused by elevation change or by curve or by that refractive rate of the cloud from each angle with the light source being different. I mean, I wouldn't assume that at all. I would do more.
Okay. Well, I think looking at things in a distance, if you did it repeatedly, all different conditions. Like I'm driving through Sacramento, Central Valley, California right now, and you can see it's super clear. You can see all the way up. Sierra's behind me. You got the Central Coast mountains in front of me, and you can see, and there's clouds everywhere too. And you can see the clouds are just skimming the tops of the mountains. If you stopped and just took angle measurements, you can see, is that comport with that 2,000-foot peak of the mountain, and that cloud just at the same level, and then the distance away that I know I am from there, because it's pretty easy to see the mountaintops, what mountains they are, and you know how far they are because you have a map. And that doesn't work. If you keep on doing these measurements, you keep on getting values that show that they're lower than they should be all the time, never higher than they should be. That would be a clue.
The problem is it's not a measurement, though. You're taking an angle measurement to an apparent location. That's not a measurement. You need an actual location. Like when you go in Home Depot and two construction workers measure a 2x4, they're not arguing for 10 years on how long the 2x4 is because they have actual position. This thing you're doing, that's why we've been arguing with it for 10 years, because you're just pointing to not actual positions, apparent positions. It could be anywhere. You don't know. You need to get an actual position. That way we can be like the construction workers in Home Depot and not have to even, it's not a debate. You put a tape measure up to a 2x4, everyone can see the lines, boom, that's it.
Okay. Well, the answer to that would be then in differential measurements. That really, if you're not familiar with that technique, will give you the refractive value at any elevation above the surface to the object.
No, I know that stupid method that you always try to use, and that does not work. You need you never get an actual position out of that. You need to get an actual position.
You get very close to it because you'll get by the rate of change of the position that it changes as you go higher. It might not change at all. If it doesn't change at all, then you know that is the actual position. By the way, you would agree though, right? If it didn't change at all as I go higher.
No, I don't agree.
If it didn't, if there was refraction,
strongly disagree.
Well, that means so you're saying the angle to the object is changing, and we know that refraction is based on angles of incident, which is a primary component of refraction. And if it didn't change as you went higher, then you would say you have to say there's no refraction because it's a law of Snell's law.
I wouldn't have to say that. I wouldn't have to say that.
Well, you don't have to say it, but Snell does. He's more.
Nobody has to say that because when you're standing on the ground, you're looking through a layer of you're looking through an optical corridor. There's a specific amount of temperature, pressure, humidity, atmospheric turbidity. There's something going on in that optical corridor. Once you raise up and do the stupid thing you want to do, there's a new optical corridor with new stuff in it.
Right.
So yes.
And a different angle.
Yep. There's a different angle and a different optical corridor.
Sure.
It's not like it's the same if you had the same optical corridor, I would say, oh, Zanuck, you're right, but it's not.
Well, you're going through the previous optical corridor. You're using
You're not looking through the previous optical. The first optical corridor is gone. Now you're into a new optical corridor, and you have new optical effects, which could cause the thing to appear in a new apparent position.
Okay, fine. Then you have a very narrow scope optical corridor that doesn't overlap with any optical corridor you previously were looking through, and it doesn't change. And you keep on going up, which is at a different angle to that object through the differential medium. And if the object doesn't change position ever up to, say, 20 or 30,000 feet, let's say, almost looking straight down to
changing your optical corridor and you're changing your angle.
How about, okay, here's the absolute. Would you agree that if you looked right above the object, that it would be right below you? If you had a plumb line and you dropped it down from a helicopter and the plumb line looked right at that spot,
you shouldn't agree to that, first of all, because you guys have curving plumb lines. So if I was you, I wouldn't agree to that.
We've angled plumb lines.
Curving. They curve.
there curve to the plumb line?
You have curving plumb lines in it. You didn't know that?
Why would it be a curving plumb line?
There's no curving plumb lines. This is just Jeremy doing his level thing again.
It's called the Schehalian. All right, guys. Good talk, man. I'll see you later. No, I'm not joking. This guy's straight
Jeremy
up
really
sucking
doesn't
out.
like it when fat.
No, you
I
just
like
suck.
your
No,
explaining
don't come
curving
in
plumb
ad
line.
homing, bro. Don't do that. Don't
So
do
if you had
that.
a long plumb line, you're saying that would curve? Because why?
It's ridiculous. Obviously, it doesn't.
I'd like to hear Jeremy's cartoon description of that one.
Well, Jeremy's no longer with us. He left.
Did anyone remember how he justified it or how he explained it?
What he's referring to, Zanuck, is the fact that over the last few days we've had a running conversation. Jeremy, I think, literally can't imagine a curved surface that is everywhere perpendicular to plumb. That's
Right.
his fundamental problem. Yeah.
Okay. I kind of thought it might be
No.
something like that.
Let's not talk about him while he's not here. He's just fed up because, I've heard him say it. He's fed up of stuff like when we drop something, for example, John, do we know that it's falling or not? Stuff like that, like double speaking,
Yeah, no, I
nonsense.
understand. I understand the nonsense that you try to put meanings to words that they don't have. Jeremy and others, you maybe, I can't know. It was somebody else I was talking with who has this idea that just because in general relativity the every point on the surface of the Earth has an acceleration relative to inertial reference frames, that would have to translate into the Earth expanding. And it's just a failure to understand that in relativity, inertial reference frames are local and they move differently in different places.
No, it's not a failure of understanding. When I pick up, let's say I pick up my phone now, right? And I drop it. Do I know for sure that it's my phone falling to the floor?
Are we really going to do this?
Well, this is the nonsense that certain people are fed up with, and they really, that's why that's what we're having this convo, right? Certain people are fed up with the double speak and the stuff that is just nonsense.
Oh,
like
that's-
you can't even admit that when I pick up my phone, it's my phone falling to the ground. So
no,
Are you
that's
saying that
the double speak is that's such an incredible accusation, because this is coming from people who want to make definitions of words more important than the meanings that we attach to them. And yeah, when I say that you can't, I'm sorry, Zanuck, I'll just finish up quickly. When I say that you can't say that it's the phone that is moving toward the Earth, I'm just referring to the fact that there's no such thing as absolute velocity. That's all I'm referring to.
well, you can say it any which way you want, but we absolutely know in our reality that when I pick up the phone from the table and I let it go, we know for sure that it's falling, right? That it's falling to the floor and not the floor coming up.
Right. I know that I
know.
know you say right, and I say yes. I know that you know that. The fact that you're wrong doesn't change the fact that you know it.
The fact that I'm wrong, the fact that I know I'm right means that I'm wrong? Is that what you're trying to say?
No, what I'm saying is, once again, no, shut up. There is no such thing as absolute velocity. Therefore, you can't say this thing is moving and this thing isn't. You can't say that because there's no such thing as absolute velocity.
Yeah, but I wasn't talking about absolute velocity. I was talking about the fact that I can know when I pick up my phone from the table that it's next to me right now. I'm looking at it. And I know when I let go of it, if I hold my hand and arm, like shoulder length, and I drop it, I know it's going to fall to the floor. I know for sure that it's not the floor moving up. Can you say that with certainty, John?
No, what I say is it doesn't matter. In certain reference frames, it's the floor that's moving up. In other reference frames, it's the phone that's falling down. In other reference frames, they're both moving. In some reference frames, one is chasing the other. In some reference frames, they're moving toward each other. But what I do know is that the distance between them is getting smaller. That's what I can say for sure.
Yeah, this is and excuse me for saying this. This is the I don't know, psychobabble, if you want to call it,
Well,
of
can we
trying
break
to
it down?
explain.
I think we
Yeah, that's
One of
something
their
we set
favorites.
up with.
can we break it down a little bit, SC? So we both agreed that the distance is getting smaller. That we both are in agreement. All of us, all three of us, John, you, and me, right, SC? The distance is getting smaller with time, and
When you
there's
drop
a change. Right? Can I at least have a common ground we all can agree on?
When things get closer, do they get closer? Yeah.
They're getting closer, and they're getting closer at a increasing rate. So
Oh,
there's
until
a
they reach terminal velocity. Okay.
there's a velocity, and there's also a change of velocity. Can we go that far? Point two. I'm at like 3 or 4 points, and then we're going to find a common ground that we all agree on. SE, are you with me? This like John said, the distance is changing. They're getting closer, and they're also getting closer at a increasing rate, acceleration. So there's a velocity and there's a change of velocity. Yes?
Does that in any way change what is going on? Is my phone going to the floor, or is the floor going to my phone? That's the question.
Yeah, bear with me on this. So we do agree on those 2 points. I know what you're saying. You've said this for a while, and I know there's a difficult. Jeremy's made it really, graphically apparent that he has a problem with things accelerating up the surface, accelerating outward to all objects because they're not falling. The Earth is accelerating to get, and I'm just trying to show where that it's not double speak. It's just understanding of the context of what these words mean. So you agree that the objects are getting closer together, the phone and the ground. You also agree that the rate at which they're getting closer is increasing. So you have acceleration. Now the point is, which is the ground accelerating upward or is the phone going downward? Well, if the phone is going downward, and you can actually show graphically, physically, that there is no forces acting on that phone because all objects anywhere near it would all be falling at the same acceleration rate, regardless of its mass. We need a force to accelerate, so they're basically inertial. If they're inertial, then how can they be accelerating? Well, then the answer is because the ground is coming upward. There's actually a change of direction due to that bending and warping of space-time. And that's not doublespeak. It's just saying that explains this paradox. How can something be accelerating and not have any forces acting on it? Well, it's a simple explanation. We've complicated it root, but simple explanation that the ground is accelerating upward. That doesn't mean it's moving upward. It means that there's a change of direction because velocity is made up of two components, a magnitude and a direction. We're not saying that the magnitude is changing. We're saying that the direction is changing because they're bending and warping, turning. This turning of your movement through space and time, there's a turn, and that's an acceleration, and that's why we see and talk about the Earth accelerating upward, not the object accelerating downward. How about that, John?
That is the biggest.
Yeah, no, that was good. I do think, I think the problem is, of course, it's everything you said is true. I don't think it'll get through any better than anything I said. But the thing I like to point to, one thing that I think is at least compelling is that there are devices that measure absolute acceleration, things that can tell you for sure if you're accelerating or not. And if you attach one of those things is in your phone, so you can get an accelerometer app for your phone and you can hold your phone and it will tell you that you're accelerating upward at 9.8 meters per second squared. Now, I can tell you what that means. It doesn't mean the Earth is expanding. It doesn't mean any of that. But your phone will tell you that you are accelerating upward at 9.8 meters per second squared. And if you drop your phone and then you look at the readout of the accelerometer during the drop, it will tell you that your phone was not accelerating during the drop. Now, make of that what you will. But that device measures absolute acceleration.
Pretty well said. And SE, so I just want we're defending our accusation upon us that we're double speaking. So what John just said, do you have a problem with that? There's a reason why we're saying what we say, and that's based on what he just told you. Does that make sense, SE? Just so we Just so you're not telling us that we're double speaking.
No, what you said before, I call that improv science. You're making up stuff, warping it space, times, and complete and utter nonsense. Like personally,
Right.
since you asked, all I have
Okay,
to
what
say
about,
is I picked up my phone and it fell to the ground.
what about
Let's see who
John?
wins.
John said there's a meter. There's actually a tool, like a scale is a version of that as well. Your phone has these components that can actually tell you whether you're accelerating or not. And when you drop it, it's not accelerating. When you're standing on the ground, it's telling you there's an acceleration happening. How do you explain that?
My wife just cracked the joke, and she never does listening, right? She says, as you dropped your phone, I felt the earth moving up. So even my wife is laughing, bro.
Sounds like a song, right, from the 60s?
You managed to make my wife laugh about it, and she thinks this is crazy.
Well, then it has not
It
been
is
in
crazy. It's
vain.
silliness.
That's all I'll
I
say.
feel the earth move.
What about SC when you drop like if I dropped if I dropped a 2x4, right, and it's say 4 feet long, right? It's all the whole 2x4 is going down, I guess. And now what if it's and that would be just like following a plumb line. Now what if it's 10 feet long, then 20 feet long, now 100 feet long, 200 feet long? Are the two ends of the 2x4 moving down at a different rate than the middle? Or,
Well, now you're not going to like the answer, so I'm not sure I'm even going to give it because
I don't.
it's an answer that only makes sense in relativity, and it's referring to an effect that you'll never actually measure. So I'm not even going to go there. I'll just stick with the Newtonian answer, which would be that the rigidity of the rod would ensure that the two ends accelerate at the same rate.
Yeah, but like, are the two ends of the rod at 100 feet, 400 feet, 800 feet, 1,000 feet? Are those two rods, um, parallel to every other point along the two ends parallel to every point along the piece of wood?
Well, I'm not sure if you're referring to this. Let me just point out that in Newtonian gravity, the bottom end of the vertically held pole will feel a stronger gravitational pull
Oh no, that's a
than the
mistake. I had it.
top end.
I
Is
had it.
that what
I
you're
had it.
referring to?
No, I have it in the horizontal orientation.
Oh, horizontal. Oh, then I'm not sure what you're. I'm not sure then what you're
If
getting at.
if all parts of the 100-foot 2x4 fall at the same rate, would that mean that they're all at the same elevation?
Well, the rigidity of the rod kind of gets in there at some point. I mean, technically, the two ends of the rod will try to kind of compress the rod because they're both falling toward the center of the earth, but that's a very small effect. The middle of the rod is a little closer to the center of the earth than the ends if you hold the ends at the same level. And so there's all sorts of things, that you could worry about, but the rigidity of the rod, which isn't perfect, will keep the rod, accelerating basically at the same rate.
You see what they're doing there? It's double speak.
Well, no, remember the 2x4 now has ends that are higher above the surface in the middle, and it's falling with the middle plumb line. It's falling along the middle plumb line.
Which direction?
Yeah.
Which direction do things fall though?
Well, the middle is falling straight down. The ends are not falling straight down. They're making a slope path.
Yeah, they're falling in towards the center, right? So I mean, in this
Right,
idea.
you're not going to ever be able to measure that. Unless your rod is 5,000 miles long or something, you're never going to notice that. This is the whole thing once again about whether globe deniers can imagine a sphere so big that it looks flat. That's really the question for me, because it is the only claim, the only positive claim brought is that it looks flat. That's it. There is no other positive claim.
It reminds me. Well, there's tons of positive claims, but there is another. It reminds me of a test, right? That was done by these guys. They're called what's their name? Busters or something.
Mythbusters.
Mythbusters. Yeah, when they showed that the bullet drops at the same the rate that gravity predicted over the distance. They shot it over a nice level surface over the distance, and it fell and hit the ground off in the distance at the exact rate as predicted by gravity. The only issue was that they didn't take into account that if the Earth's a sphere, there would be a change in elevation from one point to the other point. So they proved, if you'd call it evidence proof, that Earth is level.
Well, they didn't. The uncertainty in that measurement would have been too small to detect the, what, a few centimeters at most, probably, curvature of the Earth. They're looking
But there,
for timing things, and they can't distinguish
Yeah,
between
the
those.
timing
but
would be
That's
relative
that
to a
that
distance. Yeah, the
that kind
timing,
of
like
point.
if something to hit the ground, would be relative to the distance measurement. Yeah.
Yeah, but remember, the Earth is curved and its plumb lines are curved. So actually, the elevation did not change. That's the whole point of it. And people always say, well, it's got farther to go because it's no, it's not. That's not going farther. When you talk about orbital mechanics, if you shoot a bullet at 22,000 miles an hour at the surface, it will, if you can keep that propellant going out of the bullet, say it's like a rocket or missile type of bullet, it will stay, but it would not ever fall. It doesn't mean it's covering. It doesn't mean like it's missing the Earth because it's going so fast and it's got centrifugal force that's countering its weight. So its weight
Oh,
will
no.
be equaled by its centrifugal force, so it stays aloft. When you shoot a bullet and it falls, it follows the Earth curve. It's not like it's dropping down some elevation, like you're dropping it off a cliff or something. It's falling over. It's a level surface. It's level from the moment you shoot it. It's level, and every point along its path, and at the distance above the elevation is falling no different than if you just dropped it. That's what they proved.
Yeah, they measured what would be predicted in a linear path of the bullet falling in a parabolic drop due to gravity, and it intersected the level surface as would be predicted with the 9.8 meters per second squared, but over a horizontal surface.
Do you
Not
If it was
remember
a
how
horizontal.
curved
far the
surface, it
bullet
would have
went?
been. If it was a curved surface, it would have been a
Do you
drop
No,
remember?
over the
the Earth is
distance.
flat.
No, because a
You,
curved surface with gravity is the same thing as a horizontal surface with the same force applied.
Exactly. That's what I was
Horizontal bends
trying to
now.
say. Yes.
You
do you
guys all
remember
go to
the? It's not quite. I mean, it really isn't quite. If you shoot
go
the
to
bullet
Babs.
horizontally, then it matters that the Earth curves away. But you only notice it if the bullet, is going fast enough that it can go far enough before it hits the surface that you do notice. I mean, that's the diagram I put in the chat is Newton's way of explaining how you get an orbit. You throw things
Yeah.
faster and
So anyway,
faster until they're fast enough that the Earth
so there's a
falls away
flat
at the
Earth
same
proof
rate.
for everybody. And now that we know, with the MythBusters who are professionals, like real professionals, who actually demonstrate things in the real world.
Do you think
Now
we
that we
take an
know,
issue with that? We're not. Nobody's taking an issue with MythBusters. Do you happen to
right,
remember how
there's no
far the
issue.
bullet went? How far it actually traveled?
Far enough to
Far enough.
affect the
Okay.
drop over distance. But anyhow, so now that we know that there's a positive claim on the table shown to be proven, that level is horizontal, and the shortest distance between 2 points is a straight line, and that's what they measure this. That's how people make measurements in 3D reality, and they made this measurement in reality, proving that level is horizontal. Now we just need
John,
to find out what's giving us this. There's stuff on the table. But now we got to find out what's giving us this this up and down vector along with the acceleration due to, some people would say gravity. Other people would say the displacement of a heavier medium upward or lighter medium. A lighter medium upward as a denser medium goes down, increasing the acceleration through the medium, or whatever, gravity or whatever.
I got something for you, John. I want to challenge that last thought for a second. If I misunderstood it, it might be part of the problem I'm having. But I'm saying I'm going to contend that shooting the bullet over a horizontal surface with plumb lines that are all parallel is no different than shooting a bullet oriented horizontal level over a curved surface with varying converging plumb lines. The bullet will act no
Yeah.
different in my mind, no different than either way. It's not like
Yeah.
at first I had to take a step back. Oh, maybe I haven't thought of it that way before. You're shooting it horizontally and it's kind of going up towards space, but no, it's actually falling. No different than if it was over a flat surface based on the vector of gravity along its path. So,
Well, but I do think. I mean, I think I understand what you're saying, but I think you need to. First of all, we need to really make clear in our minds that we're talking about a perfect sphere, no
yeah,
atmosphere. We're going
perfect
to
sphere, no atmosphere.
shoot
Yes,
the bullet perfectly horizontally at the place that it's fired. And
right,
I know you will agree that if I shoot that bullet fast enough, it will never hit the surface of the
right,
Earth.
and
Right?
that's not because it's trying to like follow this you're aimed away from the curve. That's because its centrifugal force is going to be generated,
Right.
which will equal its weight, and it'll never fall because it's making
Well,
such a slight, it's making a turn, a change in direction such that its weight equals the centrifugal force. Its centripetal force equals the centrifugal force, and it floats as long as you can keep
okay.
that 22,000 miles an hour velocity.
Yeah, so I
Yeah,
get
with
that,
it,
but
yeah.
see, what you're doing now is you're looking at it in the rotating frame, a frame that rotates once every 90 minutes.
Oh,
I
no,
just
not
want
the
to look
rotating.
at it. I just want to look at it in the non-rotating. That's right. I mean, we're forgetting about the Earth's rotation
No.
in the
I
basic
was ignoring.
thing.
I was ignoring the rotation too. In fact, if you did
Right.
rotate,
So
that would even add more to it. That would even add more to it.
Right. So
So
in that case, when you fire the bullet, the only force acting on it in the inertial frame is gravity. And as a result, it is falling toward the surface of the Earth. And the only reason it doesn't hit the Earth is because the Earth's surface is curved, and it will go further than it would on a flat surface for the same reason. If
All
you
right. So
shoot
what? So,
Right,
so what?
but
The reason I brought this
no,
up
it's
and why
still
this reminded me of the conversation we were having is because I said extend a 2x4 to be 200 yards, like in the case of this experiment by MythBusters. There was people claiming that the two things would fall towards the center, that they would hit the ground in the center before it would hit on the two ends. But what's shown in MythBusters, which is pretty much 200-meter long 2x4, is they dropped something at one location and shot a bullet, and it fell at the rate as predicted by gravity at the other location, showing that level is horizontal. And the board,
no,
in this
see, it
case,
doesn't.
the board in this case, as I sum it up, the board in this case, the bullet hit the ground, the level surface evenly at all
Right.
points.
could have been hindered
Right.
by
No, that's
air
right. But you're just
resistance as well.
misunderstanding. You're just
yeah.
misunderstanding the precision thing. This is not that it does. I mean, we do. I do this demonstration when I'm doing an introductory physics class. You shoot something at the same time you drop something, and they hit the floor at the same time.
Welcome
But
to
that's
more
but that's
horizontal.
because you can't. I mean, because the curvature of the Earth isn't big enough to make a noticeable difference, and that's the case with the bullet as well.
Okay, John, one last time because I think we still are missing each other on this one, and I think let me just go with one more time. No rotating Earth, just the fact that this bullet is being shot horizontally level. It is following the curvature of the Earth because the plumb lines are. This is the only reason because the plumb lines are not parallel. So it's going to be exactly the same vectors along its path as if the Earth was straight. So it's not going to miss the Earth because it's traveling. It's not going to travel farther because it's traveling. It's going to hit the Earth at the same point, exactly like it would if the Earth was flat.
Well, I mean, to be fair, even as a glober, it's not though.
Well,
Right?
this is for John.
I mean,
because I think maybe this, I might be wrong, and then or I might learn.
Yeah, I just invite you, Zanuck, to consider just take the situation with a globe Earth and then just draw a straight line out tangent to the Earth at the place that you fired the bullet. And I think you'll agree that the bullet hits that line before it
yeah, I
hits
mean,
the Earth.
we have orbital velocities, right? And it's worth pointing out that the speed of a bullet is like 3.2% the speed of our escape velocity. And if you were to shoot it fast enough, it would have gone into an orbit. So it absolutely does go further even on the globe Earth model.
That makes my point. That's my point exactly. So he invoked the rotating Earth, and he thought I was talking about a rotating Earth. No, I'm talking about strictly a station. Let's say the Earth stopped, still has its gravity, just not rotating. You shoot the bullet, the vectors are changing along its path. Down is always pointing toward the center, so it's they're non-parallel plumb lines. If you transpose it and do some transfers of the geometry of this environment, it will show that the bullet will do the exact same thing over the curved Earth and land and hit at the same time as or if I dropped it. Or third scenario, if I shot it over a horizontal plane with parallel plumb lines, there'll be no difference. Those three scenarios will be the same.
Well,
That's
so let me
Yeah.
try this. Suppose you did shoot it really, really fast,
There will
right?
be a
So
difference. The
fast,
difference will be the
so
distance.
fast that it went halfway around the Earth. Well,
Yes.
let it be orbital. Shoot it at orbital velocity, right?
Yes.
If the Earth were flat, it would hit the Earth.
Correct. And it wouldn't if it would. Okay, so now
And so
back up,
that's just an extreme case of my point that
and I love
on
it.
a flat Earth it will hit the Earth
Okay,
before it hits the Earth if it's around
then,
Earth.
then consider this then, and this will be my final. And
Okay.
I like this guy. I hope you're enjoying.
No,
Not,
it's good because I know it's in good faith. I appreciate that.
so now think about this. Now we're going to shoot. Now we are rotating, and now I'm going to shoot the bullet against the rotation. So I'm going to shoot this bullet 1,000. I'm at the equator, and I'm going to shoot 1,000 miles an hour against the rotation. Now we remove any orbital mechanics, right? It's not going to have any kind of weight change because we're basically, well, it does now actually. It had more weight when he shot it, or less weight when he shot it, and has less weight as it's being shot. Maybe that was a bad analogy, but you're getting my point though. If I shot it against the rotation, it's still good.
I think in that case, it is exactly in that case, and only in that case, it's exactly the same on a flat Earth.
Perfect.
Because in that case, the bullet is literally just falling to Earth, just like it would be on a flat Earth. But in every other situation, there's going to be a difference. That's my contention.
And I said that difference, I think we have to agree then, is because of the fact that it's making taking a curved path, which is an acceleration, which would be taking away from its weight, which makes it go farther. The faster it goes, the less weight it has, the farther it will go until it has no weight. And the centrifugal force are matched, and it will just continue to orbit the Earth at 3 feet above the ground as long as you're able to keep it going at 22,000 miles an hour. Thanks, John.
Yeah. No, it's fine.
Way for explaining it.
It would be good to, I mean, it's a little hard to actually do it. Suppose you shot it at, half of orbital velocity. It's easy to calculate how far it would go on a flat Earth. It's not so easy on a round Earth because now it's in an elliptical orbit. You have to find the place of intersection and all that. So it makes it more complicated. But I assure you that what you'll find is it goes further on the round Earth than it does on the flat.
The distance would be the key factor. That's what's proven in Mythbusters. I mean, now the Globers. I mean, you guys are Globers, obviously.
Yeah, and once again, as far as the Mythbusters things go, we're just talking about very low velocities. I mean, I know it seems fast, but it's not very fast, and it doesn't
matter.
It's
not about the speed. It's not about the speed. It's just the distance. The vertical distance, the horizontal distance, and then both hitting a level surface at the same time. Proving. I mean, you guys are going to have to deal with it, I guess. But with the proof, if evidence is proof to you guys, right? You have to deal with the evidence.
It doesn't prove. There's experimental. No, but there's experimental uncertainty.
Well,
that's the thing you never fold in is the effect that you're looking for is very small, and you can't detect it in that experiment. What they're doing is a slightly higher velocity of the demonstration that I do in class when I shoot something horizontally and I drop something at the same time. There's no surprise because the Earth in my lecture hall is flat. It's flat. It's a really, really, really big sphere, and that's flat.
Then there's the Yodvos effect, which is really what I'm getting at on it, that is going to affect the east and west by the fact that it's the centrifugal force matched with the centripetal force. And eastward, you're going to get a higher, it'll hit your target higher than you aim, and westward, it'll be a little lower.
That's right. Yeah, and the Army artillery manuals specify that, right? They tell you how much lower or higher you have to aim to take into account the rotation of the Earth. Yep.
And those components are mixed as you go Yodvos, east to west, as you go. Both are a variant of Coriolis anyway. It's an apparent deviation based on rotating or accelerated reference frames. So that's why they have that. And you can see in the military manuals, they talk about every angle, every azimuth, what happens to that deviation for the artillery fire.
Right, both up and down and left and right. Yeah,
correct.
Yeah, every change in elevation on the globe would be a change in angle between 2 points.
Yes, but if it didn't work, they wouldn't do this because lives depend. They want to hit those bad guys. If they're 26 miles away on a gunboat and they don't account for, I'm a flat earther. I'm like, I don't believe this shit. I'm going to shoot it this way, right at it, and it misses it by 100 feet. They miss, and then they get a shot off, and then they sink their ship. They're dead. So that's why they do these things. It makes sense because it works and it's proven.
Every change in
Isn't it interesting that they
elevation
do that though?
would be a change in the horizontal plane, which would be a change in the angle, and would have to be accounted for. Even a gyroscope, as it goes up in the air, straight up vertically, a change in elevation, it would have to start to, just with a change in elevation vertically, would have to start to
But it doesn't.
readjust.
But it
Then the
doesn't
Earth is
because you shoot
flat.
it horizontally. No, it doesn't because the plumb lines are angled inward. You're going on a plane where every time it makes a motion forward, it moves forward, the plumb line is angled backward to keep
Yeah,
it like it's
a
going over.
gyroscope.
It looks exactly like the bullet to the bullet as a flight. Hold on, it looks exactly like to the bullet, not a gyroscope, but to the bullet as if it's going over a flat plane. The only difference is the faster it goes, the lighter it is, the farther it'll go.
I was just speaking on this globe. Every change in elevation would be a change in the horizontal reference at that different elevation point, which would be a different angle to any other object at a different place. Much like on a globe, a gyroscope that changes in elevation would have to start to tilt.
Changes in elevation would tilt. Why would a gyroscope tilt if you go in elevation?
Because it's a different horizontal tangent that it's being affected by gravity. So a gyroscope, as it changes in elevation, height, altitude, would have to start to tilt.
It doesn't though.
Well, then the Earth is flat.
No, but this means that the plumb line doesn't change because that gyroscope is oriented by the plumb line, by how you orient it to start. You're not changing orientation by going straight up.
Yeah, a gyroscope takes up space in 3D space, so the two ends of the gyroscope are at different plums. So as you change in elevation, you get further and further away from it. They would diverge more and more. And if it doesn't tilt, then the Earth is flat.
That's interesting logic. It's highly flawed. But we can go to why later. But no, I don't.
It's the same thing. It's the same thing as the 200-meter 2x4. It's the same thing as the bullet drop. It's the same thing. It's all the same.
Because I'm telling you that there's no difference between the bullet dropping and dropping it because they're, geodetics are like the study of like surveyors, for example. They would not agree with you at all because they are saying what I'm saying. Geodetics and geodesics are straight lines. Even though it's a curved line, it's a straight line. That's where QE would go, oh, you're double speaking and you're an idiot, fundy idiot. No, that's what geodesics means. It means effectively it becomes a straight line. You all the forces are balanced the entire time. There's an equilibrium. There's equipotential equilibrium all along its path.
At a point. Yeah.
Not at a point.
No, Tanks I put a video in the chat. I just want to make sure. I think this is the Mythbusters you're talking about. It's a much smaller distance than I even imagined. It looks like it's a football field or something. I mean, and
300 meters then. That's even more.
300 meters. But I mean, I guess the point is, once again, is it really that you can't imagine a sphere so large that over 300 meters you couldn't tell that? Is it really that you can't imagine a sphere so large that a 300 meter distance would? Is it really that you can't imagine
all of the
a sphere?
Is
it really that you can't imagine a sphere so large? Excuse me.
Okay,
is it
guys,
really? Let me just ask the question. Let me just finish my question.
Vertical points and the distance between them, everything that's been shown, all of the evidence is that level is horizontal, and that now we need to account for why things move at a different rate through the air, through different mediums. It could be due to displacement and this whole seeking of equilibrium, whatever. But regardless of the interaction between substances, it's been measured and provably level is horizontal, and now people have to deal with it.